I want to go through that NMSI super problem over equilibrium. So if you haven't worked it yet, pause the video and go work that problem. So this problem, you have 5 moles of sulfur trioxide that are placed in a 5-liter vessel and allowed to decompose at 400 Kelvin according to the equilibrium reaction that's given. Once equilibrium is established, 3 moles of sulfur dioxide are present. So part A, write the expression for the equilibrium constant. That's not wanting you to plug anything in. That's just what does the expression look like. So as with any equilibrium expression, it's always the concentration of products over the concentration of reactants. So for this one, K equals the SO2 concentration squared times the O2 concentration divided by the SO3 concentration squared. All 3 of those are appearing in this equilibrium expression because they're all in the gas phase. If anything was a solid or liquid, it would not appear. So just kind of keep that in mind. You're using the coefficients as your exponent for the concentration or the molarity in your equilibrium expression. Okay. Part B, calculate the initial concentration of SO3. So they told you at the beginning it was 5 moles of SO3 put in a 5-liter flask. Concentration is molar or molarity, which is moles per liter. So it's 5 moles in a 5-liter container. So that's 1 molar SO3. And you can kind of see I'm using the scoring guide as if this was an AP question. You can see exactly like how each of these parts would have been scored. Obviously, this is longer than an AP question for your FRQ. Remember, your FRQs are 10 points for the long questions and then 4 points for the short. So this one's super problem because it's longer than a long FRQ. Calculate the equilibrium concentrations of O2, SO2, and SO3. So for that, you're using your ICE table. So you started with 1 molar SO3. You didn't start with any SO2 or O2. And then you're going to undergo your change. So we're going to do minus 2x for this sulfur trioxide, plus 2x for sulfur dioxide, and then plus x for O2. Again, that x is the change using the mole-to-mole ratios for using up reactant and forming product. So then we get, for equilibrium, the SO3 is going to be 1 molar minus 2x. The SO2 is going to be 2x. The O2 is x. So when you set up your ICE table, they told you at equilibrium there's 3 moles of sulfur trioxide. So 3 moles in a 5-liter container, need my calculator, is 0.6 molar. So we know at equilibrium, the sulfur dioxide, the SO2, is 0.6 molar. And that's equal to 2x. So then we know that our x has to be divided by 2 is 0.3. So x is 0.3 moles, or 0.3, not moles, 0.3 molar. So there is our ICE table. We start with 1 molar minus 2x plus 2x plus 1x. Plugging in, because we know that this equals 0.6, we know that x has to be 0.3. Plug in 0.3 for our x values, we get our equilibrium concentration. So O2 was just x, so 0.3 molar. The SO3 is 1 minus 2x, which leaves us with 0.4 molar. So those are our equilibrium concentrations. Now plugging those in to calculate Kc, just plugging in your concentrations to your expression you already had. So the concentration of SO2 squared times the concentration of O2 divided by the concentration of SO3 squared. Plugging all of those in, making sure you're typing it in your calculator right, we get the K value, or the equilibrium constant, is 0.675. Equilibrium constants are unitless because they're just kind of a ratio of concentrations. They kind of tell us where equilibrium lies, so don't use units. Calculate Kp for this reaction. Because it's gases, we can use Kp. Remember, that equation's not given on your equation sheet. So Kp is equal to Kc times RT to the delta N, where R is your gas constant, T is temperature in Kelvin, and then delta N is the change in moles. So for this reaction, we start with 2 moles of gas and we form 3 moles of gas. So delta N is gas products minus gas reactants. So 3 minus 2, so our delta N is 1. So to calculate Kp, we do Kc times RT to the first power, 0.675 times 0.0821 times 400. We wind up getting Kp is 22.2. Again, it's an equilibrium constant. It's unitless. Okay. The reaction vessel above is cooled from 400 to 298 Kelvin. The mixture reestablishes equilibrium, but now with less moles of product. Okay, so we decrease temperature and we get less product. So what does that tell us about this reaction being endothermic or exothermic? So if we decrease temperature and that makes less product, that means decreasing temperature shifted this reaction to the product or to the reactant side. So it shifted it left. Okay, shifted it left or shifted it in the reverse direction. So decreasing temperature shifts it left, which tells us that heat has to be a product. Okay, not a product. I'm sorry. Heat has to be a reactant. Okay, less heat shifts it left. So heat is like a reactant in this equation, which means that it's endothermic. Hopefully that makes sense. If heat was a product, if this was exothermic, and we decrease temperature, it should shift it forward. Okay, so it's shifting it, thinking about heat being a reactant or a product. And same with Le Chatelier, how do we change the concentration or change the amount of heat as a reactant or product is going to shift that equation. So lower temperature shifting it left means that heat was a reactant. We decrease reactant, reaction shifts left to replace it. Okay, calculate the sign of standard entropy. So entropy is not on your AP exam anymore, but it's still part of the content that we've covered. You'll still be tested on it when we take our Unit 5-6 test. So still a very valid question. Predict the sign of entropy change. Remember, entropy is disorder. So how does the disorder change for this reaction? We went from 2 moles of gas to 3 moles of gas. So that's more disordered. That's a positive entropy, okay? Entropy is disorder. So delta S. So this is a positive delta S because we're making more moles of gas. G, the value of the standard free energy change, delta G, is positive 141.8 kilojoules per mole. So that's a positive delta G, which tells you this is not a spontaneous reaction. We could have already predicted that because it's endothermic. So it takes energy or takes heat as a reactant to make this product happen. So you've got 2 different ways to kind of know that this is non-spontaneous. It's endothermic. And then delta G is positive. So that's the positive delta G is what for sure tells you this is not a spontaneous reaction. And so we're going to calculate the value of the equilibrium constant at 298 Kelvin. We've already got the equilibrium constant for this at 400 Kelvin. And so now we're calculating a different temperature. Remember, temperature does change the value of that equilibrium constant. So this equation's on your equation sheet. Delta G equals negative RT ln K. Again, this R value is that gas constant, but now it's using the energy gas constant. So instead of 0.0821, 0.0821 is liter atmosphere per mole Kelvin. But in this problem, we're using energy units. So we're using the other R value, the 8.314 kilojoules per mole Kelvin. So keep that in mind. Just watch your units. It'll tell you which R value you need to use. So delta G is negative RT ln K. We're looking for K, so we can rearrange. Plug in delta G, plug in R, plug in the temperature in Kelvin. You wind up getting the ln of K is negative 57.3. And then you use the E function to undo that ln. So E to the negative 57.3 gives us K. So K is 1.3 times 10 to the negative 25th. Didn't ask you, but that K value is super, super small. So what that tells us about this reaction is that the equilibrium of this reaction strongly favors the reactants. Okay, remember 10 to the negative third or smaller favors reactants. 10 to the positive third or bigger is going to favor products. Okay, H, determine whether the moles of SO3 will increase, decrease, or stay the same after each of the following disturbances or stresses to this equilibrium system. So the temperature is temperature is decreased. We already said this was an endothermic reaction, so heat is a reactant. And so when you decrease temperature, that's decreasing a reactant. It's going to shift left or shift in the reverse direction. And so SO3 was our reactant. We're going to get more SO3 when this reaction shifts left. The volume is I don't know why I'm backwards. The volume of this container is increased. Okay, so remember when we increase volume, it shifts to the side with more moles of gas. or you can think about increasing volume as decreasing pressure. You need to pick one way or the other to think about the volume or pressure questions. I always stick with volume. Increasing volume shifts to the side with more moles of gas. Okay, so on this problem, we had 2 moles of gas reactant and 3 moles of gas product. So when we increase volume, it shifts forward or shifts right to the side with more gas. SO3 was our reactant, so that means that the SO3 concentration decreases for this one. Okay. And nope, still going. In a different experiment, sulfur dioxide and oxygen gases were added to a vessel at 400 Kelvin, and we have this reaction. So this is the reverse reaction, and it's decreased by 2. Okay, so all the coefficients are halved. So calculate the equilibrium constant for this reaction. So we had our K value for up above, which was 0.675 for the forward reaction. When we reverse this reaction, okay, that's like 1 over K. Our initial K value is products over reactants, which now in this equation is essentially our reactants and our products, so we're inverting the K value. So that's something to know. If we reverse a reaction, we do the inverse of the K value. So we get 1 over K. Also, what we're changing on this one is that we've halved all of our molar coefficients in that balanced equation. Instead of 2, 1, 2, now it's 1, half, and 1. Coefficients do matter in your K expression, in your equilibrium constant expression, and so it does change the value when we half those K values, or when we half those concentrations or half the coefficients. So it's going to take that whole expression raised to the 1/2 power. And so our K value for this reaction, this new equilibrium reaction, it's going to be the inverse of our initial K and raised to the 1/2 power. Okay. So 1 over 0.625 to the 1/2. And I'm getting our new K value is 1.22. Okay. Hopefully. And that was it. So that is our equilibrium super problem. It's got some equilibrium and some thermo mixed in. Super good problem to review as we have our Unit 5-6 test coming up in the next couple of weeks. So let me know if you have a question about that super problem or any parts of that, anything that was mentioned that's not clear. And look for my next video.